Good morning, students. Today we are going to have another seminar class on Klein Garden equation, which will be taken by one of my students, V. Karthik. This Klein Garden equation started in the year 1927 in Solvay conference. So that's the 5th conference on electrons and protons. In 1927, there was a conference among physicists and chemists, and both they were gathered together. At the time, Niels Bohr profoundly announced that henceforth a new science, quantum mechanics, is going to be started. So we are going to have a quantum mechanics. It's a new science that we are going to introduce. So profoundly announced about quantum mechanics, and all people accepted this one and they clapped. Nearly 29 scientists, they were gathered together. Out of 29 scientists, 19 bagged Nobel Prize. See, 29 scientists, they were gathered together. So out of 29, 19 got Nobel Prize. See, very important one. And another important one is, during the conference, the first session started with Klein and Garden. Klein and Garden independently they proposed this theory. Of course, we know 1926 Schrödinger introduced Schrödinger wave equation. We know about very well. This is about the non-relativistic equation, and he wanted to prove his equation in terms of specialty of relativity, but he could not achieve. So Klein and Garden independently they tried the non-relativistic equation using specialty of relativity, and they achieved one equation. And this equation, this will have second order differential equation both in space and time. So space, time, they are in symmetry, and of course they are going with from one system to another system with a Lorentz transformation. And the discussion went on like this. By the same time, Vladimir Fock, a scientist from Russia, he also published the same paper. So sometimes we call this equation as Klein-Garden-Fock equation sometimes. So three persons, they attempted to derive relativistic quantum mechanics equation. So during the interval, Paul Dirac, he was sitting having some cup of coffee. So Paul Dirac was sitting there. Niels Bohr came and approached him, and he asked him, what you are going to do now, what you are doing now. And immediately he said that I am going to do some research work on relativistic quantum mechanics. Immediately Niels Bohr replied, so this is what Klein-Garden did. Just now they presented a paper on the equation, and it works out very well, and what you are going to do now. And he wanted to say, Paul Dirac wanted to say, he was not satisfied with the equation. In fact, it is true, because Klein-Garden equation is applicable only for spinless particles. One. Second one is, it gives the negative probability. Negative probability cannot be there. It cannot exist. So these two discrepancies were there. So Paul Dirac wanted to get rid of these discrepancies, and he wanted to make another equation. So with this introduction, Klein-Garden equation is a starting point for the relativistic quantum mechanics, and of course we know about very well. And my student V. Karthik is going to present today on Klein-Garden equation. So on behalf of you, I invite Karthik to present the seminar on Klein-Garden equation.
Good morning to all. I am Karthik. I am pursuing my final year MSc degree in physics in Government Arts College, Melur. First of all, I would like to thank my head of the department, Dr.A. John Peterson, for giving me this wonderful opportunity. Today I am going to present my seminar topic is Klein-Garden equation. Let's move on the topic. Schrödinger developed the non-relativistic equation and also generalized the wave equation for relativistic form. So he tried. This equation has been taken from the transition in classical dynamics from non-relativistic relations. We know already about this. E is equal to p squared by 2m. We know about kinetic energy is given as P squared by 2m. Corresponding relativistic relation between the energy and the momentum of the free particle is given by this equation. E squared is equal to P squared C squared plus m squared C power 4. This is non-relativistic equation. This equation is taken from the special theory of relativistic. This is from relativistic equation. This is from non-relativistic equation. E denotes the rest mass energy m naught squared C squared. The corresponding operator is given by, for energy E is equal to I h cross dou by dt, and the momentum will be minus I h cross del. Now look at this equation E squared. So both sides are quadrilateral. So now we are going to square the corresponding operator. So E squared will given us minus h cross squared dou squared psi by dou t squared, and this will become minus h cross squared del squared psi. Substituting equation 2 in fourth in equation 2. The start in the relativistic equation for a free particles. So now this equation becomes minus h cross squared dou squared psi by dou t squared, which is equal to minus h cross squared C squared del squared psi of r comma t plus m squared C power 4 psi of r comma t. Now bring this term to left hand side. Now will equation is h cross squared C squared del squared psi of r comma t minus h cross squared dou squared psi by dou t squared r comma t, which is equal to m squared C power 4 psi of r comma t. Now going to dividing this equation by h cross squared C squared. So h cross squared get cancelled. Now h squared get cancelled, remaining 1 by C squared. Now C power 4 by C squared. So 1 C squared get cancelled, remaining m squared C squared by h squared. Del squared psi of r comma t minus 1 by C squared dou squared psi by dou t squared is equal to m squared C squared by h squared psi of r comma t. So I pull this psi by commonly out. So del squared minus 1 by C squared dou squared by dou t squared psi of r comma t, which is equal to m squared C squared by h squared psi of r comma t. Now I will, this term is square del squared is equal to m naught squared C squared by h squared psi. So this operator is called as the D'Alembert operator. The del squared is given as this term. This equation is known as Klein equation. It is invariant in space. Now we already know del squared can be written as dou squared by dou x squared plus dou squared by dou y squared plus dou squared by dou z squared. This term can be written as dou squared by dou ICT squared. Now the 4-dimensional space, first one is x1 is equal to x, x2 is equal to y, x3 is equal to z. The last one is what we call x power 4 is equal to ICT. This is it is also called as Minkowski space. Now equation 5 has a plane wave solution as, so psi of r comma t is equal to e power I k r minus omega t. Which are the eigenfunction of the operator with the energy eigenvalue h cross omega and h cross k, and energy and momentum respectively. Now we are going to differentiation equation 11 with respect to r twice. First we are going to differentiation r dou by dou r dou psi by dou r, which is equal to I k e power I k r minus omega t. Again we are going to differentiation. So I k multiple I k I square minus, so k square minus k square e power I k r minus omega t. Difference in equation 11 with respect to t twice. Dou psi by dou t is equal to minus, this term differentiation with respect to t. So dou psi by dou t is equal to minus I omega e power I k r minus omega t. So we are going to differentiation again. So minus omega multiple minus omega, minus get cancel, I square minus 1. So minus omega square e power I k r minus omega t. So now going to substitute in equation 12 வந்து 13 in equation 5. H cross squared omega squared e power I k r minus omega t, which is equal to h cross squared c squared k squared e power I k r minus omega t plus m squared c power 4 e power I k r minus omega t. Now taking the common terms are get cancelled, that will give you h cross squared omega squared is equal to h cross squared c squared k squared plus m squared c power 4. By taking the roots on both sides, now h cross omega is equal to plus or minus h cross squared c squared k squared plus m squared c power 4 power 1 by 2. We already know eigenvalue energy is E is equal to h cross omega. Now E is equal to plus or minus h cross squared c squared k squared plus m squared c power 4 power 1 by 2. Now look at this term. It gives plus or minus. That means energy can be positive as well as energy can be negative. But we are studying only all energies are positive. No negative energy in physics. All energies are negative. All energies are positive. Negative energies are meaningless. It implies that the energy of the particle can be as well as negative. The free particle in relativistic quantum mechanics will have as negative energy values. At present, positive square root is considered. Thank you.